to introduce to you Michał Eckstein, who got PhD in Krakow. Then he was doing a postdoc in different places, also in Gdańsk. But now he is entangled between Gdańsk and Krakow. Will come to Krakow soon, and now he will tell us about our recent work. And the title is Quantum Optimal Transport. So, Michał, go ahead.
Yes.
The floor is yours.
Thank you very much. It's a great pleasure for me to start this this seminar this semester. And well, indeed, right now I'm in a kind of a superposition between Gdańsk and Krakow. So officially in Krakow, physically in Gdańsk right now. Well, okay. So today I'd like to share with you some research results we got with Shmuel Friedland. I can see Shmuel is here. Welcome, with Sam Cole from Missouri and Carol, whom you know very well. Okay, so what is it all about? Well, okay, sorry. Let's see. Yes. Okay, so well, it all started in the 18th century when Gaspard Monge, quite a talented mathematician, was given a task to build fortifications. So, well, it means that you have some piled sand and you want to transform it into some given shape. And the question is how to do it optimally. What it means optimally? Well, you want to minimize, of course, the work that you invest to complete this task. And Monge was clever enough not to pursue the tedious computations that were usually invoked at this time, but he managed to do some drawings and said, okay, this is going to be an optimal way to do it. Okay, so that's the original motivation and formulation. Now in modern language, well, you use the language of probability measures and well, performing an optimal transport task means minimizing some cost, which can be whatever cost you can imagine. Well, so if you consider two probability spaces with some probability measures on it, say mu and nu, and then you define a cost function, which is a function on these spaces, okay, on the product of these spaces. Well, it can be 0 in some cases. It can be infinite if you want. You can have infinite penalty for doing something. And well, one nice example is that if y just equals to x, and you have some metric on x, which, well, you can think of it as having some space with some geometry, let's say some hills and some valleys. And you need to take into account this geometry if you want to perform some optimization to minimize your work. Okay, so the Monge optimal transport problem is formulated as follows. So if you have a map from x to y, and it's called a transport map, if it maps your initial measure to your final measure, in this sense. And then what you do, well, you take your cost function, you integrate it against your initial measure, and then you look for an infimum over all these transport maps, and the one that realizes this infimum is the solution to your transport problem. However, there is a problem here because suppose you have a measure which is just a single Dirac delta, and your final measure consists of two Dirac deltas. So imagine you just have a single grain of sand, and you need to make 2 grains of sand out of it at different places. Well, a grain of a sand is not divisible, at least not, let's say, classically. So there is no transport plan which can solve this problem. But it turns out that you can consider something more general, and this was done by probably first by Kantorovich and also by Wasserstein. Rubinstein was also involved. So the idea is that if you have these two measures, one on space X, mu on space X, and nu on space Y, then you need to consider a say big measure omega on X times Y, such that its marginals, so the left marginal is mu and the right marginal is nu. Okay. And if you have such a transport plan, you can denote all of the transport plans, all of these couplings, by this symbol gamma. Then what you do, well, you need to compute a double integral with respect to this measure of your cost function, of your chosen cost function. And then you look for infimum over all admissible transference plans, okay, so with fixed marginals. Okay, and well, okay, this is a very general problem, and you can take many different cost functions. So let me just advertise that with Paweł Chorodecki, Ryszard Chorodecki, and Tomek Miller, we had an idea how to use the classical optimal transport problem with a very specific Lorentzian cost function to study the problem of causal evolution of wave packets. Okay, but then let's get back to the, say, Riemannian case and consider just a space X with a distance function on it. And if you start with a distance function on your space, you can promote it to a distance on the space of all probability measures on this space. Okay, so, well, you just take this quantity here, you take a pth power of your cost function, take the infimum, and then you take a pth root of it. And it's always a distance on the space of all probability measures on your space. Okay, so we just recall that the probability measures are in fact the, well, you can think of them as classical mixed states, okay, on the commutative algebra of observables. Okay, so that's the idea of the say classical optimal transport. And this is very general. It's, well, this is the continuous setting. So now let's talk for a while about the discrete setting, because this is the one we are going to generalize here. So take just an endpoint set, okay, set of endpoints, and consider two probability vectors of length n, let's say PA and PB. Well, in these probability vectors, you can think of them as classical states, so probability distributions on this space X. Okay, so what's a transference plan? Well, a transference plan is just another classical state now on X times X. But this is nothing else as a classical state, so a probability measure on an n square point set. So it's just a probability vector of length n square. Okay, so take this probability vector and form an n square by n square matrix with it, just put it on the diagonal. Okay, and you have a diagonal coupling matrix. Okay, with this fixed marginals. Okay, so now consider some distance function on your space X, and well, with it you can define a matrix, an n by n matrix, just taking this formula. So you can see it will have zeros on the diagonal because it is a distance, and it's going to be symmetric. Now, once you have this n by n matrix, what you can do, well, you can recast it into a single vector of length n square. Well, you just cut it like that, and then make a harmonic and put it on the diagonal. And you have a diagonal cost matrix, which is again an n square by n square matrix. Okay, and then you can rewrite the whole classical optimal transport problem in the language of traces and matrices, which is well, very similar to what we are used to in quantum mechanics. So you take the diagonal cost matrix and a diagonal coupling with fixed marginals. You take a trace of it and look for the coupling which gives you the minimum. Okay, so that's the formulation of the, say, discrete classical optimal transport problem. All right. Well, with the help of it, you can form the p-Wasserstein distances, as in the general case. So you just need to take your cost matrix to the pth power, and then you take this after the minimum. You take the pth square root, and again, it's going to be a distance on the space of all probability vectors of length n. Okay, just two remarks. So first, if your space has a geometry of a simplex, so all of the points, the distance between all of the points is 1. Well, unless they are equal, then it's 0, obviously. If you have this kind of a distance, this geometry, well, then you see that the distance matrix will have only zeros and ones. Okay, so if you recast it into this cost matrix, you will have a matrix which has just zeros or ones on the diagonal. Okay, so this means that if you take, it's idempotent. So if you take any pth power of it greater than 1 or equal 1, you will just get the same matrix. So in this specific case, the cost, the optimal transport cost is insensitive to this parameter p. So for Wasserstein distances, you just, well, you can just take, say, W1 and then take the pth root of it. Okay, well, I mentioned this because this will be our starting point for the quantum case, and then we will eventually get back to the more general one. Well, and let me also mention that, well, of course, you can form this discrete transport problem for more general cost matrices, not necessarily coming from any distance. But then, of course, this guy won't be a distance in general because it's not. It won't even be a distance for the pure states. But if you start with a distance, you will get a distance. All right. So here's a very nice figure drawn by Karol, which gives a nice comparison and an idea. So here's the continuous case, the continuous classical case. So you have one fixed probability distribution here and the second one here, and you look for all joint probability distributions with fixed marginals. Okay, this is the discrete case. So we have some probability vector here and another one here, and you look for all, say, big probability vectors, again with fixed marginals. And now, well, what happens in quantum mechanics? Well, in quantum mechanics, you're not working with directly with the probability distributions, but with the states. Okay, so the obvious thing to do is, well, you have a fixed state rho A and another fixed state rho B, and you look for all couplings, so all bipartite states, which have fixed partial traces. Okay, so you can think this is very closely related to the so-called quantum marginal problem, which is essentially this problem that you have some fixed marginals, and you ask what are the global states, the, say, p-partite or n-partite in general, which are compatible with these marginals. Okay, so this is this setting. All right, so putting it into a more precise definition, so let's call by omega n the set of density matrices of order n. So now take any two density matrices from this set. And now consider a coupling matrix or quantum transport plan, quantum transference plans, if you wish. So this is going to be a state of order n square, a density matrix of order n square, such that the partial traces agree with the one that you have fixed at the beginning. Okay, so then denote by gamma q the set of all such coupling matrices. And note that it is always non-empty because, well, you always have at least the tensor product of the two states, obviously. And then, well, what you can do, you can take any quantum cost matrix, which can be any Hermitian matrix of size n square by n square. Okay. So this leads you to the quantum optimal transport problem in the general discrete setting, which is given by this formula. Okay, so you have your fixed quantum cost matrix, and you have your fixed marginals, and then you look for all bipartite states with these fixed marginals, and then you minimize over this set the trace, so the expectation value of this quantum cost matrix, if you wish, so the trace with this cost matrix. Okay, so that's the general setting. Now, a bit of history. So, well, let me just remind you that the classical optimal transport is a very, very powerful and very large domain of mathematics. Well, the big figure in the field is of course Cedric Villani, a field medalist, and but the quantum optimal transport problem, well, this has started not so long ago, and some early attempts, probably not the first one, but certainly one of the first ones, were by Karol Życzkowski and Wojciech Słomczyński. So they were concerned with some Fushimi distributions of quantum states, and they defined a Monge problem for them. Okay, so roughly the idea is that, well, you're not working with the quantum states directly, but you transform them into some probability distributions. And for these probability distributions, well, you can formulate the usual problem. Okay, so it's not a direct approach. It's not a direct generalization with marginals, but some specific setting. Okay, but it was one of the ideas. Then there were some different ideas. Probably the first works in this direction were by Tarlin and Maas. And then it developed quite rapidly into quite a number of papers. And this approach exploits the so-called dynamical formulation of optimal transport, which was formulated by Benamou and Brenier in the year 2000. Okay, I won't go into the details about that. So let me just say it's related to the continuity equation. So it exploits somehow the continuous version of the transport. Okay, so you have some parameter like time, and then you look for some dynamical couplings. And then there were several attempts for direct generalizations using quantum couplings, so matrices with fixed marginals. Well, okay, here's a list. It's certainly not an extensive list. If you did work on the problem and you're not on the list, then I'm terribly sorry. We have a more extensive list in our paper. Well, let me say, okay, so the basic idea is clear, that you need to optimize over some set of quantum couplings. And this set is, well, it's very obvious how it should look like. But what is not obvious at all is how to choose the quantum cost matrix. Which are the reasonable quantum cost matrix, and what's the interpretation of it. Okay, so, well, people had different motivations. So one class of approaches was to study the semi-classical limit of quantum mechanics. So this was in an infinite dimensional setting, and these were the works by Gauss, Muot, Paul, and Tagliotti. Well, another interesting approach was developed by De Palma and Trevisan, where they had a slightly different, very similar, but slightly different notion of a quantum coupling. But the advantage was that then there was a correspondence, one-to-one correspondence between the quantum transport plans and quantum channels. Well, there's yet another approach developed by De Palma, Marvian, Trevisan, and Lloyd. And they were concerned in generalizing the Hamming distance. So the Hamming distance is a kind of a distance to compare the strings. They wanted to generalize it to the quantum settings. Well, and they did it quite successfully. So our motivation was to generally find cost matrices which would yield some analog of the Wasserstein distances. And this aim was not achieved previously. Because, for instance, in these two approaches, so like these guys here, well, they had very nice cost matrices, but these cost matrices didn't lead to a distance. Well, primarily because if you have a quantum channel between two states, then well, if you have the same state, then the only channel is the identity channel. But for this identity channel, you won't get the distance, which, well, the quantity they call the distance is not really zero. So it's not a distance because it doesn't vanish if you have just the same state. Okay, well, there were other approaches where people did have genuine distances, but they were quite specific. So like this Hamming distance, or, well, there were some other contexts as well. So we were interested in asking whether it is possible to really make it directly, like from the scratch. So the idea is to take a kind of projective quantum cost matrix using singlet Bell states. So if you take a computational basis of your n-dimensional Hilbert space, and you take these singlet Bell states, coupling the A and I and J mode, then you can just take a sum of all them, with J greater than I, and you get a projective quantum cost matrix. So this thing, you can rewrite it as 1 minus swap. So the swap operator just swaps the two components of the tensor product for a just for a product state. Well, and it is indeed projective. It's a projector, obviously. So if you take a square of it, it's going just to be the same matrix. Well, this was initially Carol's idea to consider this quantum cost matrix. Later on, we discovered that there are other that there were other people developing the same idea. Well, in particular, this gentleman in 2018 considered the very same quantum cost matrix. And this cost matrix also appeared in another paper by this group. And then we learned from Andreas Winter that that he considered with his bachelor student, Mr. Reira, in 2019, the very same quantum cost matrix, and they arrived at very similar results to ours. Just that it stopped at the level, unfortunately, at the level of this bachelor thesis, and they never published these results. But it's reassuring that somehow different groups and different approaches converge, in a sense that they had the same idea, and they believe that it gives some reasonable results. Okay, so what are the results now? Why this cost matrix is really an interesting one. Okay, so just to recall, so with our cost matrix, this is going to be the notation. So TQ is the quantum transport cost, and because it's projective, the corresponding, let's say, Wasserstein distances, well, it's not yet a distance, is just the pth root of this quantity. Now, in particular, just to ease notation, I will denote the square root of TQ by W simply. So W is just W2. Okay, well, why is it so? Why this one has some particular role, this will become clear in a moment. Okay, so the first result, if you have this optimal quantum transport cost on an N-level system, so any N, well, this function is convex, it's symmetric, it's non-negative, it vanishes if and only if the states are equal, and it is unitarily invariant. Okay, so if you take any unitary, well, you get this equality. So an immediate corollary of that is these functions, these WPs, are unitarily invariant semi-distances on on omega n for any n and for any p. Okay.
Michał, maybe you
yes.
would recall what a semi-distance is. As some
Okay,
people
so
might forgot what is this.
Yes, so semi-distance is well, it's a function which is symmetric, non-negative. It vanishes if and only if the states are equal, so the arguments are equal. But it does not need to satisfy the triangle inequality. Okay, so you have to have a genuine distance. Yes, it's a good candidate for a metric.
Distance, yes.
Yes. Well, it still has some, well, even if it's not a genuine distance, it still has some nice properties. For instance, it's, well, you have this distinguishability property. Okay, so you know that if you have something non-zero, then the states are not equal to each other. So that's a good thing, probably for applications. Okay, so now the big question, is it a distance or not? But before we go that, let me give you some bounds on this optimal quantum transport cost. So first recall that if you have two states, you can define a fidelity between them. So this quantity is equal to 1 if the states are equal, and it equals to 0 if they are orthogonal. And with the help of fidelity, you define many quantum distances. In particular, the root infidelity and the Bourès distance. And these quantities are, well, they have many applications in quantum information. Well, using a theorem from this paper, 2018, we can, well, they had very similar results. So we just essentially translated it to our notation and we taken a square root. And it yields an explicit bound. So our this W, so recall it's just the square root of the quantum transport cost, is bounded from above by the rescaled root infidelity and bounded from below by rescaled Bourès distance. Okay, and moreover, this inequality is saturated if either of the state is pure. Okay, so here's an illustration. If you have a Okay, so suppose you have a Bloch ball, okay, and then you take a real slicing of it. So we set y equal to 0. You have just x and z. So you have the plane spanned by 0 and plus states. And suppose you start here. So you take a row A, which is close to the middle, but not quite. So it's this state. And then you want to move. Your row B starts at the same point, and then it moves to the plus state. Okay, so it turns out that at the beginning, this say the square root of the quantum transport cost behaves like the rescaled Bourès distance. You see, it starts here, but then it deviates and it actually interpolates to this upper bound, and it reaches the upper bound for the pure state. Because this guy is pure, then here they coincide. All right. So, well, it seems that this might be a really interesting quantity because it really interpolates between the two things. Well, this guy is a distance and this guy is a distance. So it is quite reasonable to expect that this guy should be a distance as well, although we know for sure that it's a semi-distance. And here comes one of our key results is that, well, for the qubit case, we were able to demonstrate the triangle inequality explicitly and analytically. So just to state it, for n equal to, so for the, say, single qubit transport problem, this analog of P Wasserstein distance satisfies the triangle inequality if and only if P is greater or equal than 2. Okay, so now you see that the square root is really the bound. Okay, so the triangle inequality is just this inequality. So for any 3 states from the Bloch ball, you get this inequality. So this is really a distance on the Bloch ball, and actually this square root is the limiting case. So if you take P smaller than 2, it's not a distance. So the triangle inequality fails, and in particular, it fails if you just take the quantum transport cost. Okay, so okay, this is okay, interesting, and it's somehow different than in the classical case, because in the classical case, if you start with a distance, then you take any p greater or equal than 1, and you automatically get a distance. Here, we need to start with p equal to 2. Okay, so, well, even for the single qubit case, still it's quite complicated. So we're able to show that the computation of this TQ cost amounts to solving a 6th order polynomial equation in general. And for the 6th order, there are no analytic formula. It's only up to order 4. So in general, there is no analytic formula, or maybe there is, but we cannot write it using this method. But well, we can use this this approach to get some analytic formulas in some specific cases. For instance, if you take the classical case, classical states, so just diagonal density matrices, well, you will get this nice formula. So it's just the maximum of the difference between the two eigenvalues, because these guys have eigenvalues R1 minus R, and the other will have S minus 1 minus S. And you take the maximum of the modulus of differences. And that's the formula. And there's also an analytic formula for isospectral states. So an isospectral state is just the states which have the same spectrum. So let's call the joint eigenvalue lambda. And okay, so the first state you can just, because everything is unitarily, the distances are unitarily invariant, so you can take the first state to lie here, and then the second one, well, it just differs by it has the same length, but it just differs by an angle. Okay, so this angle, let's call it theta, and here's the formula. Okay, final formula. All right, so another interesting question you can ask is, well, are there 3 states, triples of states, for which the triangle inequality is saturated? So this you can think of as a kind of a geodesic line. So the line, if you move along which the distance is really the minimal one. Okay, well, it is known that there are no geodesics for root infidelity and for Bourès distance. But on the other hand, it is known that there are such geodesics, so such lines of triplets, for the Bourès angle. So the Bourès angle is, again, something derived from fidelity with the arc cos. And we discovered that there are also geodesics for the transport metric, and they are really, really nice. Because, okay, so again, this is this real slice of the Bloch ball, and the geodesics of the Bourès angle are ellipses, so these dashed lines. And now for the transport metric, well, we don't have an analytic formula, but we can compute it numerically. And these colored lines are the transport metric geodesics. And they are really, really interesting. And you can see that there is some kind of a phase transition going on here. There's some tiny bump here, which then moves here. Here it's almost invisible. And here, if you look really close, there's a second bump. And then it smoothes out for the pure states. Okay, so it's really a complex geometry. And well, I think that's quite amazing because, I mean, usually you can think, well, what new can be said about qubits? I mean, we tend to think that about qubits we know almost everything, but this is, well, we give you a new metric for the qubits, which has some really nice properties and interesting ones. Okay, so yet another problem one can study is the problem of decoherence and the comparison between quantum and classical optimal transport. So suppose first that your states suffer from decoherence, so your marginals suffer from decoherence caused by interaction with some external systems. Well, and you can parameterize it easily by the L1 coherence, so a parameter alpha, which is actually proportional to this L1 coherence. Okay, and if the parameter alpha drops to, for 1, you just get your initial state. For 0, you just get a classical state. You switch off the off-diagonal terms. Okay, so the first result is that if you have states with more coherence, it's more expensive to transport them. Okay, so if you have diagonal states like classical, it's cheaper. I mean, this is somehow expected because if you have more coherence, there is more information in a sense that you need to take into account. So it will be more expensive to transport it. On the other hand, there's a result in a different direction, which tells you that the quantum optimal transport is generally cheaper than the classical one. Again, that very similar result was developed by Michael, Goss, and Paul well, just last year. So what does it really mean? Okay, so suppose you have two n-dimensional probability vectors, and then you identify them with the corresponding quantum state. So you just put these vectors on the diagonal, and you say, okay, that's my now quantum state. Okay, and if you do so, if you do a quantum optimal transport problem for these diagonal states, it's always going to be cheaper, or at least not more expensive than the associated classical problem. And it's fairly easy to understand why is it must be so. Well, simply because you optimize on a larger set, because now you are allowed, in the classical problem, you're only allowed to take classical couplings. And in the quantum case, well, there are many more matrices that you can take into account. So in general, you will find an optimum which gives you a better, lower cost than the classical problem. Okay, and this phenomenon we can study it in a slightly more detail. So we can study a kind of quantum to classical transition. So you can consider the decoherence of the cost matrix. So now you keep the states fixed, but you decohere the cost matrix. So again, you start with our projective cost matrix, and you when alpha drops to 0, you will get just the diagonal of it. So you have a classical cost matrix. So let me say that this guy is not a quantum cost matrix in the general sense. So it does not give a, I mean, it's not obvious whether it gives a semi-distance, at least. But well, it is a matrix, so nothing stops you from considering this quantity. So you just take this decohered quantum cost matrix, and again, you perform the optimization over all bipartite couplings. Well, and then you can take a square root of it and call it W alpha. Okay, so now consider two classical states of order 2. Because, well, if you want to compare it with the classical problem, we need to have classical states, because the classical problem is only well defined for classical states. And what you can show is that this function is a strictly decreasing function of alpha, well, unless either of the states is pure. Well, or if the states are equal, because, well, if they are equal, obviously the distance is 0, so it's obvious. And okay, here's a nice illustration of that. So you see it's for alpha equals 0, so that's this black line here. This is the classical problem. Okay, so it's actually this square root. So here your state A is this guy 0, 3, and this is, and the t moves. So okay, for 0, 3 we have just the same state, so the distance dropped to 0. Here we have a pure state, and here we have a pure state also. So in this case, well, everything collapses, so it doesn't depend on alpha anymore. But otherwise, you can clearly see that for this is the red line is the quantum problem. Okay, and then if you switch on the decoherence, it's going to be more and more expensive, and then it reaches this classical bound here. Okay, and you see it starts decohering. Well, the cost rises quite quickly. So even if you drop by just a tiny bit, it becomes more expensive. All right. The last point that I'd like to tell you about is, okay, so coming back to the general setting, because we had just one fixed quantum cost matrix. Now the question is, how general is this procedure? Can we have other interesting quantum cost matrices which have similar nice properties, and ideally which would lead to a distance? So recall that this X is just an endpoint set, which is now equipped with some distance function, and this Eij was this matrix, symmetric matrix associated with this distance function. And let's us define the following cost matrix. So you just take you just put this guy here, okay, and take a sum over I and j. So in our original proposal, this guy was just 1, okay. Now this guy won't be a projector anymore in general. So if you want to consider this analogs of p Wasserstein distances, the parameter p will also enter in the optimization formula. So you take a pth power of it. So that's the general formula. Now what we can show in full generality is that for any dimension, any p greater or equal than 1, and any choice of classical geometry, this guy is a semi-distance on omega n. So the only thing which is not clear whether it satisfies the triangle inequality or not. And we have strong reasons to believe, based on numeric, that at least for some distances, for some classical distances, the corresponding quantum problem does lead to a distance. Okay, so what we can conjecture is that for any dimension and any choice of classical geometry, if you take a square root of the first Wasserstein distance, this is going to give you a genuine distance. So, well, we are fairly convinced that this happens for if you take just the simplex geometry, because, well, we are able to show it analytically for the qubit case, so n equal 2. Then already the n equal 3 case is much more involved. We have some partial results, but then we studied some numerics, so some did it in the MATLAB, and, well, it shows fairly convincingly that it does satisfy the triangle inequality. Then we run some tests for n equal 4, and again, it seems to satisfy the triangle inequality. And then we did some attempts with some other geometries, and here it's not so clear. So I would say cautiously that it seems that some of the classical distances, you can quantize them in this way, and you will get a Wasserstein distance, but maybe not all of them. Okay, so as you see, it's well, there are quite a lot of interesting open problems here still on the market. Okay, so let me conclude with an outlook into physics, because, well, eventually we're interested in some physical questions or maybe computer science questions. So what quantum optimal transport might be good for? Well, first let me say that the classical Wasserstein distances are very useful to compare probability distributions. Well, and this you do in well, many fields, in statistics, economics, machine learning, computer vision. So a natural expectation would be to say, okay, so maybe quantum optimal transport can help compare quantum states. And this is related to quantum metrology. And so in particular, all of these fidelity-based distances, the Bures distance is used in quantum metrology. And certainly this quantum transport metric can serve to distinguish states as well. Okay, it's just the beginning of the story, so it's not particularly clear right now how one can employ it. If you have any idea, then we are more than happy to hear about it. But we think there's a big potential. And another application that was developed, mentioned very recently, is in quantum machine learning. It's called in particular the General Adversarial networks, which honestly I know next to nothing about. But what I do know is that these smart people, including Seth Lloyd and his group, claim that there is a nice application of the quantum optimal transport problem in quantum machine learning, and you can use it in a similar fashion, as far as I understand, as you use the classical Wasserstein distances in machine learning, in the usual machine learning. And well, again, as I said, we're maybe not at the level of Monge and building fortifications, but we're certainly just at the beginning of the story. So you can see that the first papers were like 20 odd years ago, and it's a fast developing field. So we think it has huge potential and many possible applications. And okay, if you want to find the details, please go and check our paper on the arXiv. Thank you for your attention.
Thank you very much. Thank you, Michał, for a very nice talk. And now we have a lot of time for discussion. And then, yes, there were already some questions posted at the chat. Maybe I will now ask, okay, first one was by John. John, would you please formulate your question yourself?
Yes, I can do that. So you had this comparison between the classical distance and the quantum distance, of course, for classical states, this bound.
Yes. Yes.
I was wondering if you know in what instances is it saturated, if it's saturated at all.
Well, obviously it's saturated if the states are equal.
Yes.
And it is saturated if the states are pure. Okay, so this you can see it on this plot. Okay. Because then
yes,
alpha equals 0 is the classical case, alpha equal 1 is the quantum case. So they are equal if the states are equal, obviously, because then it's 0. And if one of the states is pure, so you just have a simple probability vector, then it's going to be saturated. Well, otherwise, no, I don't think it's going to be saturated. It's
okay. Even for higher.
As you see, yes. I mean, we can show it certainly for the qubit case. We can show it analytically that it is a strictly decreasing function of the coherence parameter. But yes, I believe it holds for any other dimension as well.
Thank you.
So I just could not resist to plotting those points at which those bounds saturate. So twice pure points and once if they are the same. So now the next question was posed by Oliver. Oliver, are you there?
Hi, yeah. So you had this nice conjecture, you had basic numerics for any finite dimensions. So I'm just wondering if this conjecture also makes sense in infinite dimensions. Like, because sometimes things are
well, yes. Okay, so certainly the quantum optimal transport problem can be and was formulated for infinite dimensions. You can do it as well. I'm not sure if this particular cost function was considered in the infinite dimension. Maybe Shmuel can can say something more about it because he did work on the infinite dimensional case. But okay, cannot really hear you, but
yes.
Okay. So
please go ahead. Please continue.
So I think it's reasonable to expect that this is a general thing. So at least for this for the projective quantum cost matrix, I would say that yes, it should be so also in the infinite dimensional case. But then it's it's also more tricky because then you have some topological issues and you have to take this into account.
Yeah,
you have singular states and things like that. So.
Yeah,
Thank
I
you
just
very
ask because
much.
sometimes like things are easy to prove in dimension 2 and infinity, and then hard for everything else. Maybe
Yes,
infinity
yes,
is easier
that's
than
also
like
true.
7 or something.
Yes, that's also true, and that's for instance the case of the quantum marginal problem.
Yeah.
Which is well, I wouldn't say it's very easy, but it's very similar in the Gaussian case, infinite dimensional, as in the qubit case. It was solved by Jens Eisert in 2008, I believe, and he showed that it's essentially this very similar to the qubit case solved by Kliashko earlier.
Thanks. Now there is a nice question by Andreas. Andreas, will you pose it?
Yes, yeah, sure, I can say it. Yeah, so I understood that the existence of geodesics was also for two-dimensional case, where you can prove that it's actually a metric, the square root. So the question is, do you expect this to be true also in higher dimension? The existence of geodesics.
Oh, that's a good question. We didn't study it actually. I don't know, Karol, do you have any intuition about that?
Well, we have to check. So I hope it might be the case, but I'm not so sure.
I mean, there would be.
Yes, Shmuel. So maybe Shmuel has something to say. But Shmuel, you are muted. Shmuel, we cannot hear you yet. No, Shmuel. You are muted. Let's see if I can unmute Shmuel. No, I cannot.
I don't think
Shmuel,
you can.
Can you unmute yourself? Who knows how to unmute Shmuel?
It cannot be done from our side. He has to unmute himself.
Well,
unfortunately,
Shmuel.
yes. So Shmuel, there should be a button on the left lower side on the screen.
See it. Okay.
Hello, Shmuel.
Oh, yes.
So now can you hear me?
Yes.
So actually in mathematical papers that we are working on, and it's actually that every C, which is positive semi-definite and vanishes exactly on symmetric matrices, induces a Wasserstein two metric. Now, and it means that there is some sort of like, I think, differential geometry structure. Now, in this particular case, in some cases, it's exactly equal to the square root of quantum transport. That's wonderful. So you don't need to go to any, otherwise you need some fancy, some simple construction, minimal construction, and it gives you Wasserstein's metric. So there is something like that. However, it's maybe not with square root of t. The whole point, I think, in this approach, that one can use SDP semi-definite programming to compute the quantum optimum transport, and therefore life is good. But otherwise, if you can construct this Wasserstein's metric from some minimum approach, how do you compute it? That's so. I hope I answered that. So it would be more explained when we publish this mathematical paper.
Thank you. Thank you very much, Shmuel. Thanks for the comment. Are there any other questions?
Yes, so just to...
Yeah, Krzysztof Gawęcki.
I would like to... Yes, please.
Well, maybe it was sort of asked or answered even in some form before, but let me sort of put it this way. you have mentioned the dynamical version of classical optimal transport, which is sort of related to the fact that quadratic Wasserstein distance is at least formally a Riemannian distance.
Yes.
So are there such cases in quantum transport?
Well, okay, so as far as I know, these works that dealt with the quantum generalization of this dynamical coupling, they had a very similar result. So there was indeed some Riemannian metric on the space of states, and it was related to the second Wasserstein distance. So yes.
Mm-hmm. So which paper was that?
Let me see. Just a second. Transport history. Okay, so well, it might have been in this one.
I don't see
Data
the
and
point.
Oh, okay. So sorry, the second one by Data and Ruse.
Nila and Jana just went away. She was here, but she had to leave, so she cannot confirm.
Okay,
this.
okay. I think it might have been in this one, but I can check you. I can check it if you want, because
thanks.
I remember seeing the result, but okay, there are many more papers on it, so I'm not sure which exactly was it.
Thank you.
But the more complete list is in our paper.
Thank you again. Are there further questions from the audience?
I think there's one more on the chat.
By Tomasz Miller. Tomasz?
Yes, hi. Can you please go back to slide 14, where the Bloch ball was visible?
Yes.
Yes.
Good question about kinks. Yes, yes.
Ah, yes.
So they are staying.
Yes,
yes.
Yeah, they're strange. They're kind of unexpected, and that's why I started to look. Where do they exactly lie? Do you know something more about the exact location? They seem to lie on some, maybe on a small circle, you know.
Yes, I think it's actually, well, you don't see it very well, but if you look very closely to this, on this blue line, there's a second kink here. Okay, so
yeah, exactly,
first it really lies here, and then it's here. So there are really two kinks, and then they somehow merge, and they merge here exactly on the boundary. So it seems that there is some kind of a line which goes probably like that. I don't see if you can see the cursor. Can you see the cursor or not?
Oh,
maybe I can. Let me see. Oh,
okay,
yes,
Carol.
Yes, something like that. And yeah, honestly, we were equally surprised to see it. I mean, I don't know where it comes from and what it means, but certainly it's interesting.
Sorry, a short remark, Michał.
Yes.
Possibly it might be related to the fact that in our analytical solution from time to time you see absolute values. So then something is not continuous. So therefore you see the solution changes from one branch to another.
So
also you see those kinks here. You see kinks somewhere here.
There is a kink here. There is also a kink here in this quantum transport, and it comes from the fact that you have, as Karol said, you have the absolute values and you have the maximum of two things. So this formula,
right?
So it's okay. It's certainly interesting.
And perhaps last question from Eric. Eric, are you there?
Yes, I'm here. I'm even unmuted now. Okay, since you mentioned it, Michał, in the mail to me, it's not so much in the talk, but before. So what would you say are the connections to the quantum marginal problem?
Well, okay, so the quantum marginal problem in general is, okay, it tells you about the space of these couplings, which are compatible with given marginals. So there is a question, okay, about the geometry of this set. So what is the geometry of that? How big is that? And then you can ask, okay, so if you have something optimal with respect to a given cost matrix, then where does it lie in this set? And is it unique at all? Because it's not clear. So let me also add modestly that okay, we do have an explicit formula. We can compute the distance for the qubit case, but we don't know explicitly what is the optimal coupling matrix. Okay. So well, apart from the fact that it must be a coupling matrix, of course, with fixed marginals. But yes, this is an interesting problem, I think.
Let me thank all of you for presence and for interesting questions. If there are no more questions, let us now thank Michał again.
I think Shmuel has
Shmuel, a last comment, yes? Not question,
yes,
but a remark.
One comment that there is a very sort of simple explanation of quantum transport, and this is as follows. Suppose Alice and Bob share a bipartite particle, and they know their own particle. And so what is sort of the probability to have, to observe with respect some C, which is a POV positive measure. And this is at the minimum, gives you the minimum probability. So that is sort of, so this is one motivation for quantum transport, just this in terms of POVM.
Very nice. Yes, yes, yes. And of course, Eric, it is related to marginal problem, as you see, in a sense. Good. So let me thank Michał again. We used very well the time. Now it's just 3:15 in Poland. So finishing this seminar, let me already introduce to you next speaker. So Simon Barton arrived from Australia to Krakow, and he will deliver next week a talk about categories for quantum codes. So please, you can, maybe the link will be the same. If you are interested, please come. And another announcement, we are pleased to welcome in Krakow Dr. Fereshteh Shahbaigi from Iran. She arrived just today. If you are in Krakow, wish to talk to her and discuss many different problems, she will be around and we can meet here. So thanks again for coming. All the best for you. Stay healthy. The only remark is that some of us already got our vaccination, so we hope to survive till the next week. So I wish you the same. Not yet, not yet. But this week, I'm going to go. I'm brave enough to go for vaccination this week. Thanks, Konrad.
All right.
One more thing. Michał, you agreed to record the seminar. It was fine. So now I hope Konrad will be able to produce a link and post it on our webpage. So if you have, if you know any other colleagues who could not make it this day, this time, please just check in the webpage and distribute the link. Thanks, Michał, again. Good job.
Well, thank you all for coming.
Yes, thanks all for the questions, for being here, and we wish you a good spring semester.
Thank you. Bye-bye.
Bye-bye. Thank you very much.
Thank you.
Thank you, Shmuel, for
Thank
coming.
you. Bye.